Welcome to Learn with Us. This is the 11th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about the average or DC value of output voltage in a full wave and a half wave rectifier. In your previous lecture, you also understood effect of barrier potential on a transformer coupled half wave rectifier, on a transformer coupled full wave rectifier, and on a transformer coupled bridge wave rectifier, and we also solved some example problems. Now, what are the learning objectives of this lecture? In this lecture, you will study what is ripple factor. You will also understand half wave rectifier with an RC filter, and you will also study about a full wave rectifier with an RC filter. Now we will understand ripple factor. We know that the output waveform of a half wave rectifier is like this, and the output waveform of a full wave rectifier is like this. As you can see, these outputs, they are not DC, that is straight lines. Instead, they are pulsating DC with some AC variations. These are AC variations. So, these variations or fluctuations that occur within the output of these rectifiers, they are known as ripple. Now, how well a rectifier circuit is able to suppress this ripple is defined by the term ripple factor. This ripple factor is essential to measure the rate of fluctuation within the output waveform. For any rectifier, this factor should be as small as possible. This ripple factor is defined as the ratio of RMS value of the AC component or ripple component in the output waveform to the DC component in the output waveform. So, this formula is RF is equal to VR RMS divided by VDC, where this is RMS value of AC or ripple component and this is the value of DC component in the output waveform. Now we will derive the ripple factor of a half wave rectifier. We know that the formula of ripple factor is VR RMS divided by VDC. Now, the RMS value of the AC component or ripple component of a half wave rectifier is 0.386 Vp, where this Vp is peak voltage, and from our last lecture we know that the average value or DC value of output voltage in a half wave rectifier is Vp divided by pi. So after putting these values in this equation, we get Rf is equal to 0.386 Vp divided by Vp divided by pi. Now this Vp is going to cancel this Vp, so now we'll have 0.386 multiplied by pi, and after solving this you will get 1.21. So this is the ripple factor for a half wave rectifier. Now what is the ripple factor of a full wave rectifier, again the formula is RF is equal to VRRMS divided by VDC. Now, the RMS value of the AC component or ripple component in a full wave rectifier is 0.3 Vp, and again from our last lecture we know that the average value or DC value of output voltage in a full wave rectifier is 2 Vp divided by pi. So again we'll put these values in this equation. We get RF is equal to 0.3 Vp divided by 2 Vp divided by pi. Again this Vp is going to cancel this Vp, and now we'll have 0.3 multiplied by pi divided by 2, and after solving this we'll get 0.483. So this is the ripple factor for a full wave rectifier. Note that the ripple factor of a half wave rectifier is more, while the ripple factor of a full wave rectifier is less. Now we will derive the RMS value of an AC component or ripple component of a half wave rectifier. In my previous slide, I have mentioned that the RMS value of this ripple component is 0.386 Vp. Now, how you are getting this value? Here we'll use the formula of RMS value. This RMS value is the effective value of varying current or voltage. It is the square root of squared function of the instantaneous values. I have mentioned in my previous lectures that instantaneous values are the sum of AC and DC values. In this case, AC value is RMS value of ripple voltage and DC value is VDC. So now here VRMS will be square root of squared function of this AC value, that is VRRMS whole square plus squared function of this value, that is VDC whole square. Now I can write this equation like this, and since I have to find VRRMS, so this equation can be rearranged this way. Now for a half wave rectifier, this VRMS is Vp divided by 2, and we know that the value of VDC is Vp divided by pi. So if we put these values in this equation, we get VRRMS is equal to Vp square divided by 4 minus Vp square divided by pi square under root. Now we can also write this equation like this: Vp 1 by 4 minus 1 divided by pi square, because this Vp is common here and we just took it out of this under root. So now after solving this term, we get VRRMS is equal to 0.386 Vp. Okay, so this is the RMS value of ripple voltage in case of half wave rectifier. Now we will derive the RMS value of an AC component or ripple component of a full wave rectifier. In my previous slide, I have mentioned that the RMS value of This ripple component in case of full wave rectifier is 0.3 Vp. Now here we'll understand how we are getting this value. Again we will use the formula of RMS value, which is Vrms is equal to square root of squared function of AC value plus squared function of DC value, and we can write this equation like this: VR RMS whole square plus VDC whole square, and if we rearrange this equation like this, we get VRMS whole square minus VDC whole square under this. Okay. Now in case of full wave rectifier, the value of Vrms is Vp divided by root 2, and we know that the value of VDC is 2 Vp divided by pi. Now if we put these values in this equation, we get VR RMS is equal to square root Vp square divided by 2 minus 4 Vp square divided by pi square, and since this Vp square is common, so we take it out of this root, and now we get 1 by 2 minus 4 by pi square, and after solving this term we will get Vp multiplied by 0.3. So this is the RMS value of this ripple component for a full wave rectifier. The ripples within the output voltage can be reduced by using filters. Here we will discuss an RC filter that will be used for improving this ripple factor. First we will understand half wave rectifier with an RC filter. This is the circuit of a half wave rectifier with an RC filter, where this is load resistor RL, this is capacitor, this is diode, and this is source voltage. If this is our input signal, where this is positive Vs and this is negative Vs, then we know that the output waveform of a half wave rectifier is like this. Okay, this is the output waveform of a half wave rectifier without any filter. Now when this half wave rectifier is used with an RC filter, then during this positive half cycle of the input, this diode is forward biased, which will allow this capacitor to charge. Now on this waveform, it will look something like this. Now when the input begins to decrease below its peak, this capacitor retains its charge, and now this diode becomes reverse biased. So during this non-conduction period, the input voltage is less than that of capacitor. So the capacitor discharges all the stored charges through this load resistor RL. This prevents the output load voltage from falling to zero. So now this discharging of capacitor will look like this on this waveform. And for second cycle, the charging will look like this, and this discharging will look like this. Again, for third cycle, this is charging and this is discharging of capacitor. It means here this is showing output waveform with an RC filter. Now the capacitor charges through diode up to this point Vp, and after this point Vp, this capacitor gets discharged through load resistor RL. So it means we are getting this kind of waveform due to charging and discharging of capacitor. It means this is charging and this region is showing discharging. Again, from this point to this point capacitor is charging, and from this point to this point it is discharging. Again, from this point to this point it is charging, and from this point to this point this capacitor is discharging. Still, this output is not purely DC and it has some ripples. So the variations in the capacitor voltage due to the charging and discharging of this capacitor is called the ripple voltage. Okay. We know that the output waveform of a half wave rectifier with an RC filter is like this, where this point is Vp and this is ripple voltage. Now we will find peak to peak ripple voltage. For this we have to find minimum and maximum values of this ripple voltage. During discharging, the voltage across capacitor is given by the equation Vc is equal to Vp e raised to the power minus t divided by Rc. Now for suppose here the time required by the capacitor to reach from maximum to minimum voltage is T1, which is approximately equal to capital T. Now if we put this value in this equation, we get minimum voltage across capacitor, which is given by this equation Vp e raised to the power minus capital T divided by Rc. Now we assume that this Rc constant of capacitor is much larger than time period T. Now here we will use power series expansion formula, which is e raised to the power x is equal to 1 plus x square divided by 2 factorial plus x cube divided by 3 factorial and so on. For smaller values, this formula is reduced to Ex is equal to 1 plus x. Now here we know that the power is negative. So this formula is now e raised to the power minus s is equal to 1 minus x. So now this equation A becomes V min is equal to Vp multiplied by 1 minus T divided by Rc. Now what about the maximum value of ripple voltage? We know that Vp is the maximum value of ripple voltage. So Vmax is equal to Vp here. Now peak to peak ripple voltage is given by Vmax minus Vmin. Now after putting these values in this equation, we get Vp minus Vp plus Vpt divided by Rc. This Vp is going to cancel this Vp. So we have Vpt divided by Rc. We are peak to peak. Now we know that time period is inverse of frequency. So this formula now becomes Vp divided by FRC. This is peak to peak ripple voltage in terms of frequency. So this is the expression of peak to peak ripple voltage for half wave rectifier. Now if we want to find DC voltage, then it is equal to maximum value of waveform, that is VDC is equal to Vp minus VR peak to peak divided by 2. In most cases, this ripple voltage is very small, so this term becomes negligible. Now this VDC is equal to Vp. So under this assumption, this equation can be written as VR peak to peak is equal to VDC divided by FRC. I just substituted this value of Vp here in this equation. Now we know that from Ohm's law V is equal to IR, okay, and V upon R is equal to I. So here this equation now becomes VR peak to peak is equal to IDC divided by FC, because we know that here this IDC is equal to VDC divided by R, and it is load current. Okay, so this is the expression of peak to peak ripple voltage in terms of DC load current for a half wave rectifier. Now we will understand a full wave rectifier with an RC filter. We know that the output waveform of a full wave rectifier without any filter looks like this. Now when this full wave rectifier is used with an RC filter, the output becomes something like this. It means the capacitor charges through diode up to this point Vp, and after this point this capacitor gets discharged through the load resistor RL. So this line is showing discharging of capacitor. Now if I draw only this waveform which shows full wave rectifier with an RC filter, it is like this. Now this full wave rectifier is easier to filter because of the shorter time between peaks, as you can see here. Now look at this picture. As you can see, when filtered, the full wave rectified voltage has a small ripple as compared to a half wave rectified voltage for the same load resistance and capacitor value. So this is the difference between full wave and half wave rectifier when used with an RC filter. Now we will find peak to peak ripple voltage for a full wave rectifier with an RC filter. We know that the output waveform of a full wave rectifier with an RC filter looks like this, where this point is Vp and this is ripple voltage. Now, in order to find this peak to peak ripple voltage, we have to find minimum and maximum values of ripple voltage. During discharging, the voltage across capacitor is given by the equation Vc is equal to Vp e raised to the power minus t divided by Rc. Now here we assume that the time required by the capacitor to reach from maximum to minimum value is T1, which is approximately equal to T divided by 2. So now the minimum voltage across capacitor is given by this equation. Now we assume that this RC constant of capacitor is very much larger than the time period here, and we apply power series expansion formula to this term. So we get minimum voltage is equal to Vp 1 minus T divided by 2RC. Now, what is the maximum value of voltage here? We know that Vp is the maximum value of ripple voltage. So here Vmax is equal to Vp. Now, this peak to peak ripple voltage is equal to Vmax minus Vmin. Now, after putting these values in this equation, we get Vp minus Vp plus Vpt divided by 2Rc. This Vp is going to cancel this Vp, so we get Vpt divided by 2Rc. Again, we know that time period is inverse of frequency, so this peak to peak ripple voltage will be Vp divided by 2FRC. So this is the expression of peak to peak ripple voltage for a full wave rectifier. Now if we want to find DC voltage, then again VDC is equal to Vp minus Vr peak to peak divided by 2, and in most cases this ripple voltage is very small, so this whole term is negligible. It means this VDC is equal to Vp. Now under this assumption, this equation can be written as Vr peak to peak is equal to VDC divided by 2FRC, and we know that DC load current is equal to VDC divided by R. So now this equation becomes VR peak to peak is equal to IDC divided by 2FC. So this is the expression of peak to peak ripple voltage in terms of DC load current for a full wave rectifier. That's all for today. So, what are the key takeaways of this lecture? In this lecture, you understood what is ripple factor. In this lecture, you also derived RMS values of an AC component or ripple component for both full wave and half wave rectifiers. In this lecture, you also understood half wave rectifier with an RC filter, and you also studied about full wave rectifier with an RC filter.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.